Hello and welcome. Today, we're going to delve into a foundational question in computer science. Why did we need to develop artificial intelligence? To answer this, we must first look at the paradigm that came before it, traditional programming. In the world of traditional programming, when a developer wants to implement new functionalities or automate tasks, the process is quite direct. It involves writing code that contains a predetermined, explicit set of instructions. Think of things like if-then-else statements. These are commands that meticulously direct the computer's actions, leaving no room for ambiguity. If this condition is met, do that. Otherwise, do something else. Consequently, to get a computer to accomplish a variety of tasks, a programmer must provide a corresponding number of rules. For every potential situation, a rule must be written. This poses a significant challenge, especially as tasks become more complex. This very limitation highlights the core weakness of conventional programming approaches. They lack generalizability. They are brittle. They can do what they are explicitly told to do and nothing more. Let's put this in more practical terms. If you haven't programmed before, imagine trying to give someone directions to a store. A traditional programming approach would require you to lay out, in excruciating detail, every single step. Walk 100 paces forward, turn right at the oak tree, walk another 250 paces, and so on. Now, what if there's road construction and the path is blocked? Your instructions fail. More profoundly, what if you want the computer to do something that you, the programmer, don't actually know how to do yourself? How do you write the step-by-step instructions for a task whose optimal steps are unknown? This is where we see that regular programming is quite limited. It can't make decisions on its own. It can only follow the decisions you have already hard-coded into it. This is precisely why a new approach was needed. We needed a form of generalized programming, a system that is more than just a reflection of a programmer's static knowledge, a system that can make decisions from our perspective, learning and adapting as it goes. This brings us to a pivotal real-world example. Back in 1956, a computer scientist named Arthur Samuel faced a fascinating challenge. He wanted to teach a computer to beat him at the game of checkers. Think about that for a moment. How would you even begin to do that with traditional rule-based programming? The number of possible board positions in checkers is vast. You couldn't possibly write an if-then rule for every scenario. So Samuel came up with a brilliant plan. Instead of trying to teach the computer the explicit rules of good strategy, he had the computer play against itself. He programmed it to play over and over and over again, literally thousands of times. With each game, the program could evaluate which sequences of moves led to a win and which led to a loss. It was learning from its own experience. It was discovering the strategies for itself rather than being fed them by a programmer. And guess what? It actually worked. This method of learning through self-play was incredibly successful. By 1962, the computer program had become so skilled that it had even beaten the Connecticut State Checkers champion. This was a remarkable achievement. It demonstrated that a computer could learn to excel at a complex task without being given all the answers in advance. It could generalize from its experience to new, unseen game situations. This is the essence of why we use AI, to tackle the challenges that are simply too complex, too dynamic, or too unknown for the rigid, step-by-step instructions of traditional programming. Pretty impressive, right?